Hi everyone, and welcome to a new video about controller design, and we continue with the subject of root locus method. This is our example number 6. In this example I would like to discuss the design of a lag controller using the root locus method. Of course we'll look at our calculations and simulations in MATLAB to verify our calculations. So let's look at our example. What we have is a second order system, which is shown here in the diagram shortly. And this is the controller in cascade with a plant. So we have the controller that must be designed with a plant, and the plant is a second order system shown here, 2 over s plus 5 times s plus 9. So there are two poles at -5 and -9, which are already real and stable. And the controller is given by this expression, so which is the k, which is just the controller gain, times the s plus z lag, which is the 0 of the lag controller, divided by the s plus the p lag, which is the pole of the lag controller. We need to determine, of course, these three parameters of the lag controller. So for that, of course, we need the design specifications. So let's look at our design specifications for this example. We need an overshoot which must be less than 0.08, so 8%. And there's a steady state error specification for step input. It must be reduced 5 times compared to the P control system. That means the following. If I rewrite it down in a little bit mathematical form, that means that position error of the lag control system must be 1 over 5 times, so 1/5 of the position error, so error position of the proportional controlled system. So we need, of course, first determine what's actually the error in the proportional control system, and that must be reduced by a factor of 5. That's actually what is the second condition. So let's look at our first step. Step 1 is, of course, in our solution is determine the design point. It will, of course, allow us to determine then the parameters for our controller. So from the overshoot of 0.088%, I can use the damping ratio formula again, and then I calculate the damping ratio, which is very close to 0.63. Now, besides the overshoot, I don't have any additional information about the speed or other specifications. So what you normally also have in these specifications is settling time or rise time or other parameter, which will allow you to determine, for example, the real part and the imaginary part in a more unique way. In this case, I look at my controller, I mean the plant, and this has a pole at -5 and pole at -9. So in this case, before we will start with the proportional controller first, that will be our reference to go to the lag controller, I can say the following. The P1, which is the first pole of the plant, and the P2 is the second pole of the plant, the average of that one will be the real value of our design point. That means these two poles will make actually a root locus, so locus of these two poles will cross each other at -7, and it will stay actually at -7 as the real value. So that means I will take the sigma of d, which is the real value, as -7, which is just the average of these two poles. Now from there I can use then the geometry again, and I can say, okay, the omega d, which is the imaginary part of our design point, it must be sigma d, the absolute value of that one, times the tangent of arc cosine of zeta. So I will take first arc cosine of zeta, which is just a phase, an angle, and tangent of that angle times the 7 here, that will be the 8.7 for our imaginary part. So collecting these values, we can then determine the dominant closed loop poles for our system. And we assume that these poles, which is given in this expression, will determine the dynamics of the system. We approximate this system using these two poles, which will be then given by -7 plus or minus j 8.7. Now from here I will take, of course, a design point, and we will select the one with the positive imaginary value, which is then here designated as Q1. So Q1, I will have a design point which is now called Q1 is -7 plus J8.7, and I will use this to determine the parameters of the lag controller. So let's look at it in more detail here. What we have is then the design point Q1, which has a real part -7, imaginary part of 8.7, and we have the two real parts of our pole, which is the -5 and a -9. And these two poles will have a phase contribution that will of course need to be satisfy our root locus equation for angle criterion. We will see that shortly. So let's look at our next steps. So what we have then in the following step is the situation of P-controlled design. So we first start with a P-controlled design. That is actually the reference. So what we say is the controller is just a K, so just a gain. So the root locus equation is then given by very simple 1 plus again the loop transfer function is equal to 0. And since the controller of course is K, I can say okay, loop transfer function is the controller times the plant, which is then K times the plant, which is then a little bit simplified this expression for the loop transfer function. Now if I now rewrite, I will then substitute this in here in the root locus equation. We will have the following situation. Now if I now isolate the K from here, so just first step is place the 1 to the right hand side of the equation, will be -1, and then isolate the K, I will have this expression. Now the next step is evaluate your value of K, which is the proportional controller gain in this case, at a design point which is already determined, -7 plus J8.7. That means the following. So K evaluated at S is equal to Q1, just substitute Q1 and Q1 where you see actually an S. Now if you substitute it in the actual form, you will have this expression +5 and then again the Q1 and a +9. Now if you simplify this a little bit, you will have this. So it will be -7 and of course the 5 +5 will be in effect -2 for the real part, and here we have the -7 and the 9 will be +2 for the real part. The imaginary part are exactly the same. So if you now want to calculate of course the value of K, which is the magnitude, I need to take the magnitude of this expression, which is a complex expression, so I will take the magnitude. So that will be the absolute value of your controller gain K. That is again the very familiar standard formula. We just take the length of this expression, first term here in the numerator, times the length of this second expression, second term in the numerator, and the 2 is just a real value, so we just keep it like this. So if I calculate this out, I will get a very close to 40. That means I have a controller now designed in a very simple form. K is equal to 40. So that's our controller, P controller. That's actually our reference. So what will now happen is we will see what kind of final value we will have, and also our position error for this P controlled system. So let's look at it. So position error of our P controlled system, which is now here designated as E sub P comma pro, which is the proportional controller. So if I look at the expression for that one, it means actually the following. This is called the position error, and the K sub P comma pro is the what is called the position error constant, and we will need to determine that one to calculate the position error for the P controlled system. So how we calculate the K sub P of the proportional controller, which is then given here as the limit of S goes to 0 of our loop transfer function. This is only valid if you have a unity gain feedback configuration, and this formula in this form is also valid if you have of course a unit step input or just step input. That is actually the case. If you have a unit for example unit ramp input or unit parabolic, you need to add a S for the ramp input and an S squared for the parabolic input, but it will be determined and discussed in another video about the lag controller design. So if I just substitute the value for ls, which is just this, in here, and I will then in the next step evaluate it in more detail by substituting the value of k, which is already determined, and then substitute the value of s is equal to 0, do the math for yourself, you will get 80 over 45. What I have done is 2 times 40, of course, and just here for s 0, and also have s for this 0. So you will see this in more detail. And it will be 16 over 9 and approximately 1.8, 1.78. That's actually our proportional controller position error constant. Now, if I now use this formula, what we have is the following. I will have 1 over 1 plus 16 over 9, and it will be 0.36. That's actually an exact value. That means the following. If the input of the system is a unit step, just a unit step, where you make a step with a height of 1, amplitude 1, then the final value in the unit step response will be, this is the response, which is the output y, will be the input minus the error what you have. That means the following. 1 minus 0.36 will be this one. So this is actually what you will read in your step response in the final value or the steady state value. So this is the final value of our P controlled system. So let's look at our next step, which is then step 3, which is the design of our lag controller. So lag controller design. So the position error for the lag controller design is given by this expression, which is very similar for the lag controller and the proportional controller, because this is just a generic formula and it holds also for the lag controller. Only if you have, of course, a unity gain feedback configuration, or also if you consider the position error or the step input error. Now, if I now want to again calculate the position error for the lag control system, just specifically for the lag controller system, I will again use the formula. Before I can do that, we require, of course, 5 times reduction in the position error compared to the P control system. Thus, we have the following formula. The lag controlled system, the error of that one, divided by the proportional controlled system error of that one must be 1 over 5. And if I just substitute the values in formula for this expression for the error, position error for the lag controlled and position error of the proportional controller, just this one. Now, if you rewrite this a little bit, you will get this expression: 1 plus the position error of the proportional control system divided by 1 plus the position error constant of the lag control system must be 1 over 5. Now, I know this already, which is already calculated in the previous discussion. I can then say, okay, the position error constant of the lag control system must be then 4 plus 5 times the position error constant of the proportional control system. This is just the math from here. Just you rewrite this and you will get this expression. If I now substitute for this Kp comma pro, I will have then the following value: 116 over 9, which is approximately 12.9. Now, then I will have the following: the lag controller 0 and the lag controller pole has a specific ratio which will be determined by actually our reduction in our position error. So the formula is as follows. If you look at the position error constant of the lag controller divided by the position error constant of the proportional control, so the position error constant, the ratio of that one, will be the ratio of the lag 0 and the lag pole. So that means the following: if I know the ratio of the position error constant, which is already known here, so 116 over 9 divided by 16 over 9, that will be also the ratio of the lag 0 and the lag pole. So I will have then, if you do the math here, you will get a Z lag divided by the P lag of 7.25. That means the following: if you have some value for the P lag, you will have 7.25 times that value for your Z lag. That means in this case, you already know that the P lag, the lag controller pole, will be closer to the vertical axis than the zero of the lag controller. So if you just select a value for the lag controller pole, for example, in this case 0.1, or of course minus P lag is minus 0.1, then you will have the Z lag of 0.725. That will be the lag controller 0. You might ask why I take the 0.1, another different value. Of course you can take 1, maybe 0.5, maybe 10, maybe a large number. But what we want is, you will see that shortly, what we want is that the phase contribution of our lag controller is very close to 0. The lag in a sense will always contribute a negative phase to our system. So negative phase contribution means actually that the stability will be reduced and that the system will have maybe some other problems in speed. But I want, of course, reduce, that's actually the whole basis, I want to reduce the position error, and I'm really interested in other aspects. So I want to get rid of a lot of analysis and also details by placing actually the 0 and the pole very close to each other, that the 0 phase contribution and the pole phase contribution are not exactly to each other, but very close to each other, so such that the phase contribution is not that much for the lag controller. So if I move on, you will see what this happens. So then the lag control is then given by this expression. If I just, of course, know the 0.1 and the 0.725, you will have this. And we will assume that the K is just 40. Of course, you can recalculate this using just the S plus 0.725 divided by S plus 0.1, and then keep this as a unknown, and then calculate again using the design point Q1, and you will see that the K will be very close to 40. So that analysis actually not done here. So our controller gain, lag controller gain, I mean the lag transfer function, is then given by this expression. We have the gain, and it's 0 and a pole location as shown here. So let's look at it in more detail in our diagram. What we have is again the Q1, which is our design point at -7 and J 8.7. We see the two poles of the plant again, -5 and -9, and we see the Z lag and the P lag. The location of the P lag was chosen, was selected at -0.1, and the other one, the 0 of the lag, was calculated using the ratio of the position error constants. Now we have now determined our lag controller. We will of course simulate and verify this, but let's look at our position error of the lag control system in more detail. What we had, of course, this expression. We have now the KP, which is the KP of lag, which is of course this one, and this is not the gain anymore, but the lag controller. So if I now substitute the values and just evaluate this for S equal to 0, I will have the following, and I get 116/9, which is exact same as we have calculated. So it is in agreement what we have done, again approximately 12.9. So then we have, if you do the math here, you will get a position error for the lag control system of 0.072. That means this is the error we have, but what we have, of course, in our file form. So if the input is to the system is unit step, that means the R input is a unit step, the amplitude of 1, then the final value of your unit step response, which is the Y, will be the input minus the error what we have here calculated for the lag control system. That means 1 minus 0.072, which will be 0.928. That is the value we will see in our unit step response. So this is the final value of our lag controlled system. So let's look at the next steps. We would like to, of course, check the phase contribution of the lag controller for sure, if there is really the case, as we have discussed earlier, that the phase of the lag controller was very small or very small negative value. So let's check that. This is our lag controller, already determined, and this is the diagram again in more detail with the phases. Phi1 for the phase contribution of the pole at -5 and other one for the -9. We have the phase contribution of the lag pole and the phase contribution of the lag 0. Now all of them can be calculated, and we will use angle criterion for that one. So that means minus phi1, minus phi2, and the phi lag, which is then that phi phase of the lag controller, will be this one. And if you work it out for the lag controller, will be of course 0 and a pole, and the 0 will of course contribute a positive phase, and the pole will have a negative phase contribution. That's actually the reason why we have a minus sign in front of this phi1 and phi2, which are just the pure poles of the plant. And the phi of the lag controller, the pole of the lag controller, is also minus, which is the pole. So this is what we have, and I already mentioned that the 0 and the pole must stay close to each other, but the ratio is still 7.25 according to our specification, such that the phase contribution of the pole and the phase contribution of the 0 of the lag controller are approximately equal to each other, but not too negative. So if this is, for example, calculated minus 110, and this must be, for example, 108 approximately, then the phase differential is approximately approximately 2. That will be of course a -2 phase contribution by the lag, but that's really minimum. So if I now calculate, again phi1 is the phase contribution of the plant at -5, the other one is -9, and this is for the lag written out in more detail. And we would like to of course check if this is really the case for this lag controller. So let's check that. Phi1 is this is the phase, is again calculating this one is more easily by doing 180 degrees minus the arctangent of this height divided by the length, again shown in more detail, which is 103 degrees. Now this one is of course a phase which is smaller than 90 degrees, so we can just use directly arctangent. Arctangent of the height divided by this length will be 8.7 divided by this length will be 777 degrees. So if I now correct the values also for the lag 0 and the lag pole, lag 0 is here, which is actually this distance divided by this distance, and then arctangent of that one, and then 180 degrees minus what I have actually just mentioned. This expression, I will get 126 degrees. Now for the pole, we're in a similar form, which is again the half circle, 180 degrees, minus this angle, this small angle here, which is then the arctangent of this height divided by this distance, and it will be written out here in more detail, and it is done 128 degrees. So what you see is that the phase of the lag and the phase of the 0, as mentioned earlier, are very close to each other, that the phase contribution of this one is in total for the lag just -2. So this is very small. So let's look at it in more detail for the angle criterion. Again, minus phi1, minus phi2, plus phi z of lag, minus phi p of lag, which is the pole, and that must be of course minus 180 degrees. But if I just substitute the values, this is already, this one, the first two terms are already minus 180 degrees. So the phase contribution of the plant is already minus 180 degrees. So this must be, of course, in theory, exactly 0, such that this condition is valid. But if I look at this one, this is the phase contribution of the lag only, and it's just -2. So it is still very close to minus 180 degrees. That's actually what you most of the time do for the lag controller design, that you just ignore, or not ignore, I will say, you assume that the phase contribution is very small compared to the phase contribution of the other phases, so that it is very small, and you will have actually no really design errors in this one. So that's actually the check for the phase contribution of the lag controller. So the lag controller, again, the phase contribution is very small, and at this point really need to remember in a design of lag controller. So let's look at it in the simulation results. So Locus plot and the unit step response of the closed system with P controller. We just start with that one, and I will just call it G of Pro. and it is of course 40. We have determined that in our calculations. So let's look at the root locus plot and the unit step. Root locus plot is shown here, and these are the assumed dominant closed loop poles. You can see that the location of that one here is -7 plus 8.72i. So it's actually very close to what we had. So what we had -7 plus j instead of I, of course, it's the exact same. 8.7. So it's very close, and it confirms our calculations. And if I look at the damping ratio, which is then here 0.626, which is also very close to 0.63. So in summary, we have the damping ratio and also the design point, which is very close to what we have used in our calculations. If I look at the step response, which has an overshoot of 8.02, so I can assume that this is just 8. So it is according to specifications. So 8 is actually what we maximum was allowed. And I also see that the final value is 0.64, which is actually what we also have calculated from the error. So in total form, overshoot is 8% approximately in this case. The final value is 0.64, but the error then, let's say error, for this case, the 1, because it's unit step input, minus 0.64 will be 0.36. So that is the error what we, of course, need to reduce by a factor of 5 in the lag control design. We also see the settling time is approximately 0.54 seconds, and the settling and the rise time is approximately 0.17 seconds. We will discuss these two also shortly, but these are of course not the design specifications. The overshoot and the final value, or the steady state error, are what we really need to consider in the first place. So let's look at our lag controlled design or lag controller, and I will just give it a G lag of 1 so that I have some room for tuning. And that was the controller. And let's look at our unit step and the root locus plot. You can see that the root locus plot is not really changing. It's still approximately the same shape actually as the P controlled design. And this is actually where the 0 is of our lag controller, and this is our pole of our lag controller. And they are really close to each other, such that the phase contribution is very minimum. Now you can see the following. The design point, if I look at the design point, it is approximately -6.8. So it is a little bit different than this -7 for the real part. And for the imaginary part, it is plus 8.56 J, and what we had, of course, was J 8.7. So it is a little bit shift in the design point. So that's actually very predictable, because we will have also a 0 and a pole in our system. So it is not exactly what we have, but it is not that far away what we initially have as a design point. What is of course surprising here is in the damping ratio, of course, is just 0.622. So in total 0.622, which is very close to 0.63, and design point is also very close to what we had before. If I look at the unit step response, I see that the final value is 0.928, which is what we have calculated. But I can see there is no overshoot in the system, which is of course a little bit of surprise in this case, because we assume that there is at least some overshoot, but at max 8%. So there is no overshoot. So it's a 0 overshoot. I might say, okay, that's a very nice result. But I can see that the settling time is now over 5 seconds, and also the rise time is 2 seconds. So this is the time, settling time, and also the rise time has increased a lot compared to the design with the P control. So I can see that this design is, in terms of speed, is definitely not the best design. So the final value is okay, and the error is now 0.072. It is 5 times less than what we have before with the P controlled design, but the speed is definitely not the best option here. So we can try now, and in this case, of course, the design is complete, so it is complete. We can of course say this is what you can use for your specifications, because the time was not really the situation in this example. But if we want to, of course, speed up the system, which is possible because we have some headroom for our overshoot. So let's look at the tuned lag controller in the next phase. So I have just called that GLAG2, and you can see I have made the gain here from 40 to 35, and the 0 of the lag controller is changed from 0.725 to 4.27. So in summary, lag controller 0 is moved from this value all the way here, so it's actually 6 times to the left hand side of the complex plane, and the gain is reduced by 5, so 40 to 35. So I've made 2 changes. I just played around with the controller tuning tool of MATLAB, and I've seen that this is actually what you can get at best if you of course use the headroom of your overshoot. So if I have this, I can see that the design point of course should change a lot in this case. So the dominant closer poles, assumed dominant closer poles are these two, and if I look at the location, it will be of course approximately in this case minus 5.1 and then plus J 7.1, and damping ratio is then 0.581. So these are of course a little bit different than what we had before. So these are the values. We had of course initially 0.63 here, and then it was minus 7 plus J 8.7. So you can see that there is a remarkable change in our design and also in our damping ratio. But let's look at our settling time and the overshoot and the other parameters in our unit step response. I can see the overshoot is exactly 8, so I have just used complete headroom. And I can see that the settling time, this is okay, but I can see that the settling time is approximately 0.66. So it is a lot faster than the controller, the system with the controller GLAG1 for initial design. I also see that the rise time is much smaller, so also speeds up the system using this controller. And I can see that also this is much better, of course, in terms of speed. But I can also see that the final value is a little bit closer to 1. So the error what I have now is also smaller than the error with the lag control system in the initial design. Of course, we needed the reduction of 5 times. So if you have, of course, a reduction of 6 times or 7 times, more than 5 times, that's also fine. So it's all better. So what we have in total, in summary, the overshoot is 8%. The final value is 0.985. That means the error, what we have is then now 1 minus 1 because of the unit step input. 1 minus 0.985 is 0.015. And we had before, with the lag controller design, with the GLAG1 initial design, was 0.072. So this is definitely a lower steady state error. So let's look at the summary of the simulation results. What we have is then 3 plots. We have the blue line, which is actually the closed-loop system with the P controller. This is the orange line, which is the closed-loop system with the lag controller design, actually the initial lag controller, and the yellow line is the one we have tuned, so this is actually the second lag controller. So what you see is then the steady state values. Let's first check that one, the 0.64 for the blue line, which is the P controller design. This is the first lag control design, but you can see that the final value is exactly as before, and the tuned value is closer to 1. So if I want, of course, exactly 1, I really need a pure integrator in this case. You can also see that the overshoot is now approximately 8%, and also the settling time is as shown here as before. And you can see that again, the orange one, this is much larger in settling time than the yellow one. So we have tremendous improvement in our speed. So if I want to check that in the table, this is the controller, the proportional controller GLAG1, and this is the tuned one GLAG2. You can see that what is changing. So this is the proportional controller, the first column. The second column is the initially designed lag controller, and this is the lag controller 0 and gain adjuster, which is a tuned lag controller. And these are the values. So we have 8% approximately for the overshoot, and the rest was as given. But I want to, of course, reduce this error by 5, by a factor of 5, which is done here actually. But I've seen that the settling time and also the rise time was very large. So I want to use the headroom I had for the 0% here for the overshoot. So I did that. I used the complete headroom, and I reduced it almost by a factor of 10 for the rise time, and also approximately a factor of 9 for the settling time. So that's a really tremendous improvement in speed, and I have also the final value which is close to 1, and also the error which is then less than what I have here. So I will then see again, this is my very large, the rise time and settling time for the initial design of the lag controller, and I should go for this design, and that will of course give the best result in terms of speed and also the steady state error. So that's actually the lag control design for this example. Of course, you can do other adjustments. You can maybe say, okay, let's change the pole maybe to 0.2 and then adjust the other parameters. That can be also done. So there are many ways to discuss and design this system according to the specifications. I encourage you to play around with the MATLAB so you can see what's actually happening, and it will of course give you a lot of insight and also see what is possible, what is not possible. Alright, this is the example about the lag control design using the root logs method. I hope it is clear for you what you can do, what you should do, or also maybe what you might not do in specific cases. We will continue with other design examples, lead controller, lag lead controller, and other topics about electronics, math, and other scientific and engineering subjects. So if you have any questions or comments about this or on any other video, please let me know and I will try to answer them as soon as possible. Thanks again for your attention. See you next time and take care.